Hello everybody and welcome to the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today, we're having a race. More specifically, we're going to take three round objects, a solid disk, a hoop, and a solid sphere, and allow them to roll downhill from rest to see who wins the race, to see which object gets to the bottom first. Or, of course, possibly they all have a tie. We have to find that out first, right? So, this particular problem involves both linear and rotational motion because the objects both have to go down the hill, so that's linear motion, so they're moving from one location to another, but also they're going to spin or rotate as they go. So this kind of rolling motion is a combination of two things, straight line and rotational motion. And in order to properly solve the problem, we need to incorporate both of those ideas. So that means we have a lot going on for us. Now, what we're going to do in this particular case is we'll set up the original equation for all the objects, and then we'll note where it gets different for different objects. And when we do that, then we'll be able to tell who should win the race. As an extra bonus, we will go ahead and solve the specific case for one of the objects. We'll do that for the solid disk, given a set height. Now, we're going to assume going in that each object has the same mass and has the same radius. We may or may not find out that that matters, but let's do the problem first. So here's our setup. We have solid disk, a hoop, and a solid sphere, like that. They're going to roll down the hill. And the thing that's different about them is their shapes. Now notice their masses and their radii are identical, but their shapes are different. And because the shapes are different, that implies something about how they will rotate. More specifically, the idea of rotation, or more carefully, the resistance to a change of rotational motion, is called moment of inertia. And it's the equivalent or analog of mass being the resistance to a linear change of motion, or linear straight line velocity. So that's the idea. And which object has the larger resistance to change of motion? We'll see if that matters. All right, so how do we set up such a problem? This is a question about velocities or speeds. And therefore, our first good guess for solving a problem like this should be energy conservation. So let's do exactly that. So energy in equals energy out. Now, what I'm going to do is set up an equation, again, in general terms to talk about how this will work. And then we'll do this in a very specific case of the solid disk. Let's talk about general terms first. So at the top of the ramp, or the incline, each object has the same mass, the same radius, and they're released from rest, which means none of them have any kinetic energy of any kind. They're not rotating, they're not moving forward, therefore no kinetic energy, whatever that kinetic energy might otherwise have been. But they're also a height h, straight up. Now notice, by the way, the height is a straight height, vertical height. It's not the height along the incline. That's not what we're looking at. We're looking at height above, because gravitational potential energy doesn't care about incline. Gravitational potential energy only cares about vertical height. And that's what we're going to have in play here. So, since they all have the same mass, I'll use the same symbols. So, the mass of the object will be m, the height is h, g for acceleration of gravity, as usual, and potential energy then, at the beginning, is mgh. So we start off with that kind of energy. Now, when the object makes it to the bottom of the incline, it won't have any more potential energy. It's used all of its potential energy and turned it into kinetic. What kind of kinetic energy does it have? Well, it has two kinds. It is moved forward, therefore linear kinetic energy, and that is 1/2 mv squared, like that. But also it has rotational kinetic energy, the energy of rotating, because it is spinning, right? And we have to include that. We cannot ignore that. So 1/2 I omega squared is the formula there. Now, remember, I stands for moment of inertia. Again, that's the resistance to change of rotational motion, or similarly, the analog of mass for linear motion. And omega is rotational velocity, or rotational speed, which is the analog of linear speed. Now, what we've got written up here at the top are three separate formulas relating the moments of inertia for these different shapes. And as an extra bonus, we've got the rotational velocity written in terms of velocity and radius. Now, because the objects all have the same sizes, they're all going to have the same rotational velocities when they hit the bottom, or at least the formula is the same, I should say. Not the same value, but the same formula. So that's not going to change. So the omega squared will be the same formula. But the I is kind of interesting here. So everything else is the same, but let's think about this. What we're going to take is a set amount of energy and split it apart into linear kinetic and rotational kinetic. The larger this term is, the more it takes up, the less will be left over for this. And the slower the object will be going. Does that make sense? Think of it this way. If you go to a store to buy something and you've got, say, $100 to spend, you can spend $100 on one item and get a really good expensive item. Or you can split that up into, say, $50 each for two separate items. What that does then is it decreases the amount of money you can spend on one item. Or we could take all of our energy and spend it on just one item like this, which would be the case if the objects were moving without any friction, if they were just sliding down the hill. Or in this case, because we're making them rotate, we have to split the energy into these two pieces. So the larger this piece is, the smaller that piece ends up being, and therefore the smaller the speed. Which means the larger the moment of inertia, the slower it goes. The smaller the moment of inertia, the faster it will go. All right, so let's compare little formulas here. The hoop has a formula of mr squared. The disk has 1/2 mr squared. And the sphere has 2/5 mr squared. Now let's think for a second. Which of these fractions is smaller? 2/5 is smaller than 1/2, and both of those, of course, are smaller than 1, which means the solid sphere wins. Now notice, by the way, we didn't have to solve the entire problem. We could stop at this point. Now, yes, can you go and solve the problem? Of course you can. We will for the disk in just a moment. But you don't have to. You can stop at this stage and already make that argument that the solid sphere has to win this race, assuming everything else is equal, it's a fair race and all that kind of business, right? But if it's a fair race, the solid sphere will win every single time. Now, it's not going to win by much compared to the disk, probably, because these two fractions are not very far apart. But it is going to win. This 2/5 is smaller. It has less of resistance to rotational motion, which means there's more energy to be put into linear motion. All right, so that's the first thing. Now, let's go ahead and actually solve the problem for the solid disk. And then, once you've seen how it works, you yourself can try it for the solid sphere and the hoop. All right. So our equation looks like this. mgh equals 1/2 mv squared plus 1/2 I omega squared. So that's our conservation of energy equation that we've derived for this situation. All right. So if we're doing the disk, we have to note two things. First off, moment of inertia of the disk is 1/2 mr squared, like that. And the rotational velocity of the disk at the edge of the disk, more carefully, is v over r, like that. And by extension then, omega squared is v squared over r squared. Okay. This is a trick that we can do to solve rotational problems. If you have something beyond a trivial rotational motion problem, one of the best approaches is to turn it into something that looks like a linear motion problem. How do we do that? We substitute for things like moment of inertia and angular velocity. If we can do those things, put that in here, then we can make sense of it. So let's do exactly that. So let's sub. So 1/2 I omega squared becomes 1/2 mr squared. Notice I have the half show up again because these are two separate halves, right? They don't cancel or disappear. And a v squared over r squared, like that. Okay, what does that give us? 1/2 times 1/2 is 1/4. We have an m. We have a v squared. And then notice the r squared here cancels r squared there. We don't have to worry about it. In other words, the radius doesn't matter. At least in theory, the radius doesn't make any difference. Now, if you're doing a problem where the wheel is so big that it barely starts to move before it even has a chance to because it's so large compared to the incline, you might have an argument. Or you might have an argument if the wheels actually do experience something like a resistance from the air. So say the air drag is very large, then of course you might have an issue. But we're not doing that. We're going to assume that air drag is not important and all other these considerations don't matter for us, that everything will work out fine this way. So let's do that. So notice what we've done though. We took the rotational kinetic energy term and made it look like a kinetic energy term. Now the fraction is different, but that's because of the shape of the object. The shape of the disk gave us an extra 1/2 here. Now if we had used the sphere, for example, instead of the disk, we'd have a fraction of 2/5 in this place. And then our fraction over here would also be correspondingly different. But we're doing the disk. So solid disk gives us a 1/4 mv squared. Now, let's take it and put it back into this equation. So, mgh is now equal to a 1/2 mv squared plus a 1/4 mv squared, like that. All right. Well, 1/2 is the same as 2/4, right? So 2/4 plus 1/4 is 3/4, if you will, mv squared, this. So we have this equals this here. Now notice something else that happens. Mass is again the same on both sides. Now again, we are assuming that something like, say, air drag doesn't matter. It's negligible. And in that case, we don't have to worry about this as an issue. When you have real objects and really long inclines and so on and so forth, you can start to create situations where the air drag might become might matter, and therefore we would have to account for this a little more carefully. We're not doing that. We're assuming a much simpler sort of case here. But that means that on this side it's GH then, and this side is just 3/4 v squared, like that. Turn this around because we're solving for v. V squared equals 4/3 GH, and therefore v equals the square root of 4/3 GH, like that. So that is our algebraic solution for the disk. Now again, if we're using the hoop or if we're using the solid sphere, this point here is where it will be the difference maker. That fraction specifically, instead of 1/2, we'd have a fraction that will be 2/5 for the sphere. It'd be no fraction at all, just be 1 for the hoop, and so on and so forth. You can imagine a variety of different shapes and sizes of objects that would go there, specifically shapes. All right, let's do the calculation just to show how this works. So 4/3 multiplied by 10 meters per second squared, and we said 10 centimeters or 0.1 meter, like that. And this is a square root, so put a 1/2 power on it like that. Go ahead, grind away our calculation, and we end up with 1.15 meters per second as our answer. Okay. Now, for point of comparison, what if the object slid downhill without any friction? In other words, what if it didn't have to roll? And again, we're ignoring air drag and such things. But what if we didn't have to use up energy to make the object roll? And that would be the equivalent of sliding downhill with no friction. What would happen then? Well, the solution would end up being 2GH. This term here wouldn't exist. This would be gone. And our solution would be 2GH. So, what if no rolling? Then our solution will be 2GH, like that. And if that looks familiar, it should. This is the solution for an object that simply falls in free fall. There is no rolling, of course, for an object in free fall. It doesn't matter. So if we were to do that for these cases, then it's 2 10 meters per second squared for G, 0.1 meter for the height. Again, take the square root of everything like that, and your solution would be 1.41 meters per second. Compare these two results, here and here. Notice that because we needed to use energy to make the disk rotate, the net speed ended up being less than if it had been sliding downhill without any rotation at all. So in other words, making an object rotate requires energy, right? We've just done physics work, if you will, to our object. Gravitational potential energy, in fact, is the culprit. It's the one that did part of the work to make the object rotate. Now, part of the other work went into, of course, into making the object go downhill in the first place, right? But in any case, that's what happens. If you have an object that's rotating and moving forward at the same time, the kinetic energy has to be shared in some fashion between those two parts. You don't have one or the other, you have to share it. And that's why we get what we get. All right, everybody. Technical assistance for this show comes from C.D. Gauchow and Sophia Turner. Funding for this series of videos is provided by the University of Mississippi and the University of Southern Mississippi. I am your host, Dr. Christopher Cirola. Thank you for your attention, everybody, and clear skies.